Hi, I'm Samya Yagati, and I'm a first-year PhD student at UC Berkeley, advised by professors Natasha Crooks and Jan Stoika. It's an increasingly important problem today to do cloud-based machine learning without the cloud learning anything about what you're doing. Today, I'll focus on a subcomponent of that, secure distributed sparse matrix multiplication. Sparse matrices have a lot of zero values and few non-zero values. Sparse matrix multiplication is used a lot today in scientific computing and machine learning. For example, we might represent input text data as a sparse matrix. In machine learning, the scale of the data involved means that matrix multiplication is often necessarily distributed, adding to the complexity. As a starting point, I'm focusing on sparse times dense matrix multiplication. Sparse matrix multiplication is different from dense times dense matrix multiplication, which requires us to multiply every row and column of the input matrices deterministically. Since we can leave out a lot of zero-valued entries when multiplying sparse matrices, we can achieve much faster multiplication algorithms. However, the algorithms are no longer deterministic. They depend on the locations of the non-zero values in the matrix. We know that when a program executes, it leaves a trace of memory access patterns. With dense times dense multiplication, that trace is the same for every pair of matrices. For sparse times dense, however, the trace changes depending on the matrix structure. Here, two almost identical phrases lead to two different data access patterns in the dense matrix, meaning that we can distinguish documents just by the access patterns. These data access pattern leaks are a security issue. As we saw, attackers can use these traces to reconstruct input data up to entire text files or images. In an untrusted cloud setting, which is typical for machine learning today, this is a real threat. Data-oblivious techniques transform programs with data-dependent memory access patterns into programs with deterministic memory accesses. Our key insight is that we can use something called block diagonalization to transform sparse matrix multiplication into something that mimics the deterministic pattern of dense matrix multiplication. We can permute our sparse matrix to a block diagonal, so all non-zero values are in dense blocks along the diagonal. We also permute the dense matrix, so the math works out. Then we multiply those blocks with blocks of the dense matrix in a deterministic pattern. Finally, we permute again to get the final product. So does this algorithm outperform a baseline of treating the sparse matrix as dense and just doing deterministic dense multiplication? Our prototype analysis shows that yes, even at relatively small matrix sizes by machine learning standards, we get wins, and these wins increase rapidly with matrix size. This work is one step towards the goal of end-to-end data-oblivious machine learning systems. Assuming we solve this problem, there's other components that we need to make oblivious, like the data input pipeline and embedding tables. I'm excited to hear your thoughts. Thank you.